the statement number 1. As molar mass of K is higher than that of sodium, melting point of potassium is greater than that of sodium, right? This is about the melting points of metals, right? This is about the melting points of metals. Melting points of metals, right? So we have to compare the potassium and sodium, right? What are the major stuff we have to consider here, right? Melting points of metals depends on the metallic bonding strength. That is what we know, right? So what we know is when metallic bonding strength is high, your melting points of metals are high, right? Melting point is high, right? This is the theory we are going to use here as we are discussing about melting points of two metals, right? There are 3 factors affecting to the metallic bonding strength. What are the 3 factors? Right? Factor number 1, number of electrons released to electron C. When it is high, your metallic bonding strength is high, so that the melting point is going to be high. Number 2, size or the radius. Size or radius of cations in your electron Z, right? So when that is low, the size or the radius is low, your metallic bonding strength is high, so that the melting points are high, right? When considering D block metals, right? Only with D block metals we have to consider the third fact. We have to consider the third fact, that is the ionization energy, ionic nature. It says when ionization energy is low, you can release more electrons to electron C, so strength of electron C increases, so that the metallic bonding strength is high. So your melting points are going to be high with such, right? These are the points you should go through, right? Let's come up with the potassium and sodium, comparing the potassium and sodium, right? So both the potassium and sodium are releasing only one electron to the electron C, right? So both K and sodium are group 1 elements. So release only one electron to electron C. So we have to consider second fact there, right? Fact number 1 is constant for both the sodium and potassium. The second fact, radius of the cation, right? When it comes to radius or the size, right? We know the K plus is larger than the sodium plus. Sodium plus is smaller and K plus is larger, right? Sodium plus means only 10 electrons are there. K plus means you have 18 electrons there. So as the radius is smaller with the sodium, its metallic bonding strength is high. Because of this effect, right, we can write the metallic bonding strength of sodium is higher than potassium, right, as the size is smaller. So that your melting point of sodium is higher than that of potassium. Sodium is the greater melting point than the potassium. So let's go to the statement again. As molar mass of K is higher than that of sodium, melting point of K is greater than that of sodium. No, melting point of K is lesser than that of sodium, right? So this says the statement is false. Statement is false. Right? Statement is false. Right? Okay. So that is the review for the statement number 1. Right? Let's discuss about the statement 2. It says even though phosphorus is with Ns2Np3 somewhat stable electronic configuration, its electron gain energy is exothermic. Right? First it says phosphorus is with Ns2Np3 stable configuration. Let's discuss about that thing, whether it is true or false about the configuration of phosphorus. Right? Phosphorus. Right? It is a 15th element. Right? So its configuration is going to be then after the neon configuration, it should have another 5 electrons. This configuration comes up with 10 electrons. Another 5 is there. So 3s2, 3p3. So the configuration comes with the general form of ns2np3. Right? So the first part of the statement is true. The first part of the statement is true. ns2np3 kind, right? So that n is actually the right your row, right? Your period number. N is the period number, right? So we can write n is to np3, right? Where n equals to the period number, right? Okay, the first part is okay. Second part of the statement. Its electron gain energy is exothermic, right? What we know about the first electron gains of these atoms. When it comes to first electron gains, right? We know only three atoms, only three atoms are with endothermic electron gains. Only three atoms are with endothermic, heat absorbing, the positive electron gains. What are those? Those are beryllium, magnesium, and nitrogen due to the presence of stable electric configurations, right? Like this, no? in terms of stable electron configurations, right? Atoms are not keen to change their configurations there, right? All the other atoms, all the other atoms are keen to gain their first electrons. All the other atoms are with exothermic, or one can say negative first electron gains. Other than beryllium, magnesium, nitrogen, all the other atoms are with negative first electron gains. So phosphorus comes under this. So phosphorus comes under this. So so phosphorus should have a exothermic or negative electron gain. Right now? So phosphorus comes up with a negative first electron gain or the exothermic value. Let's see what that statement says again. Even though phosphorus is with NS2 NP3 somewhat stable configuration, yes, this is coming to somewhat stable configuration, still its electron gain energy is exothermic. Yes, the statement is true. This is somewhat stable configuration, still it comes with a exothermic negative first electron gain. The statement is true. Right? Statement is true. Right? So we can say, we can take the second statement as a true statement. As a true statement. Right? Okay. So that is the review for the statement number 2. Right. Let's discuss the statement number 3. What it says. See, the distance between the second and third lines of partial series is equal to that of fourth and fifth lines of Lyman series. Right. Let's discuss about this thing. Right. This is about the hydrogen spectrum. Right. The question is regarding the hydrogen emission spectrum. Right. So let's come up with the sketch here. Right. So if you think of this kind of a hydrogen spectrum, right, I'll take this direction as the energy increasing direction. Right. So at the highest energy region, at the UV region, you will see the presence of Lyman. Presence of Lyman. Right. So at the visible region, which is with less energy than the UV, right, the first 4 lines of the Balmer series appears. First 4 lines of the colorful lines of the Balmer series appears at the visible region. Then you have the IR region, which is with lower energy than the visible. There you could see the partial bracket and fund series. So I'll write the partial. That's the question involves only those things, right? So that is how the regions appears with the series of lines. And if you were to consider the Lyman series of lines, the Lyman's first line could be represented like this. The Lyman's lowest range line, the Lyman's second line, third, fourth. I'll write 5 lines of Lyman like this. Going towards the higher energy region, the gaps between the spectral lines decreases of a considering series of lines. When it comes to visible, so how to write the visible? Just take the second line onward from the Lyman. Just take the second line onward from the Lyman and write and paste that thing at the lower energy region than the Lyman, right? So take the second line onwards from the Lyman, copy that thing and paste it here, right? So this is the right, copy the same gaps, right? This is the Bahama series. This is the first line of the Bahama, which is known as H alpha, red colored. H beta is the second line, right, of the Bahama, which is green in color. H gamma, blue colored third line, and H delta, fourth line, which is purple, violet in color. When it comes to partial series of lines, what you should do is just take the third line onwards from the Lyman, copy that thing and paste at the IR region, right? So it looks like this. Right? Clearly maintain the lines, gaps, right? So this is the first line of the partial, second and third. I have just written 3 lines. That is enough for this kind of a question, right? So see the statement again. The distance between second and third lines of partial series. Second and third lines of partial. These 2 lines. Right? Is equal to fourth and fifth lines of Lima. Fourth and fifth lines of Lima. So just take the whole partial series, then you would get the idea clearly. So if you take the whole partial series I have written here, right? Actually, the partial series, how we are supposed to draw. Just take the third line of the series and copy paste that thing at the IR region. That is what we are doing, right? So that means this is the region. We had just copied and paste there at the IR region, right? So you clearly see the second and third lines of partial, that distance between those lines is actually equal to the fourth and fifth lines of the Lima, right? I just took this third line and copy paste that thing as the partial region, partial lines. So distance between the fourth and fifth lines of Lyman is equal to the distance between the second and third lines of partial. So your statement is true. The statement says the distance between second and third lines of partial series is equal to that of fourth and fifth lines of Lyman. Yes, the statement is true, right? Distance between, right, fourth and fifth lines of Lyman series is equal to distance between second and third lines of partial series, right? So the statement can be taken as a true statement. So your statement number 3 is true. Statement 3 is true, right? So that is the review for the statement number 3, right? Let's discuss the statement 4, right? De Broglie wavelengths of heavy particles are always smaller than those of lighter particles. Right, this regarding the de Broglie's wavelength. See, de Broglie wavelength, right? So what is the equation related to the de Broglie's wavelength? So de Broglie's wavelength is equal to the Planck constant divided by the momentum. Divided by the momentum. Momentum means the mass into its velocity. Mass into the velocity of the particle. So this is the de Broglie's wavelength. That equation with the de Broglie's wavelength, right? And this one is a constant, right? The Planck constant. H is a Planck constant. It's a constant. Always a constant value, right? It's equal to 6.6 into 10 to the power minus 34 joules per second, right? So de Broglie wavelength depends on the mass of the particle and the speed of the particle, right? Is the mass of considering particle and the speed of the particle, which together can be referred to as the momentum, right? Is regarding the de Broglie wavelength, right? So one can simplify this equation as the lambda is proportional to 1 over mv, as it is a constant. We can get rid of that with the proportional sign, right? So this is the de Broglie's relationship. So the statement says de Broglie wavelength of heavy particles are always smaller than those of lighter particles. They are saying when m is high, they are saying, right? Heavy particles means when m is high, no? Right? The heavy particles means the mass is high, no? Right? They are saying when m is high, always the lambda is high. Lambda is low, sorry. They are saying when m is high, they are saying always the lambda is low. No, when the m is high, normally the lambda is low. The m is high. When the m increases, yes, lambda decreases, as those are with some inverse relationship. But remember, you have a v as well. You have a v as well. You have a v as well, right? So, but this is not always true, right? This is generally true. This is generally true, right? But not always true. But not always true. Not always. Why is that? If you have to think of a particle with a very low velocity, this is the exception. This is the exception. If you are to consider a particle with a very low velocity, right? When considering a particle with very low speed, right? When considering particle with very low speed, then For that, lambda could be high. Lambda could be high. Lambda would be high. For a particle with a very low velocity, lambda could be high because it is also with a inverse relationship. So generally, when m increases, lambda decreases. Okay, but not always. When considering particles with very low speeds, speeds which are very close to zero, in such occasions, right, you can have a very high lambda value. Even though m is high, even though m is with a very higher weight, right, still if the velocity approaches 0, 10 to the power minus 3, minus 4, minus 5, kind of very low velocities, that multiplication will get a very low value. Even though this is 1000, if this value is 10 to the power minus 9, minus 10, kind of a very low velocity, then this will be a higher value. Simply, not only the mass matters for the de Broglie wavelength, speed also matters, right? That is the idea. So the statement, de Broglie wavelength of heavy particles are always smaller than those of lighter particles, that is false. Generally true, but as always term appears, we have to take that as a false statement. Right now? Okay, that is the review for the statement number 4. Let's discuss about the statement 5. Right, what it says. Along a period left to right, shielding effect of atoms increase. Along a period left to right, shielding effect of atoms increase. Right, that is the statement. Let's discuss this regarding the shielding effect. Shielding or screening effect. Right, actually for screening or shielding, right, two kinds of electrons matter. Right, shielding is done by right, two types of electrons. Kinds of types. What are those? Number 1, inertial electrons. Much of the shielding is done by the inertial electrons. So we say the contribution is actually 1 unit of contribution. Greater contribution there from the inertial electrons. But not only those guys, but also the own shell electrons. Basically, the contribution is a bit smaller than the inertial electrons, but there is a contribution there for the shielding from the own shell electrons as well. Right? So what happens when going from left to right of a period? Right? When going from left to right of a period, inertial electrons won't change, but own shell electrons increases. right? Inertial electrons won't change, but potential electrons increase, so that shielding will increase by 0.35 units, right? Because of this, shielding will increase. Shielding effect will increase. Even though by a smaller extent, still it will increase, right? So that is what you should know. Actually, going towards right of a period as well as going down a group, in the both occasions, shielding effect will increase, right? That is all about the statement number 5. So we have to take the statement 5 as a true statement. We have to take the statement 5 as a true statement, right? Along a period, left to right, shielding effect of atoms increase. Yes, that is true, right? Let's discuss about the statement number 6, right? See what it says. No contribution from the unstable and less stable resonance structures for the resonance hybrid. No contribution from the unstable and less stable resonance structures for the resonance hybrid. Let's discuss about that statement, right? This regarding the resonance structures and resonance hybrid. Right. There's no contribution from the unstable resonance structures to the resonance hybrid. That is what it says. Let's discuss. I'll come up with an example. Right. Let's take the resonance structures of kind of N2O. Let's copy that. Right. So the most stable resonance structure of N2O looks like this. The most stable resonance structure of N2O, right, is the most stable, right? Then you have, right, some more structures, right, can be written like this. Right, this is also a stable structure. There's no reason for this guy to consider as less stable. This is also a stable structure, but this is more stable because you have two reasons to become stable here. Because adjacent indicator atoms coming up with opposite charges, as well as the most reactive oxygen coming up with the negative charge. So two reasons are there to become stable, right? Here only one reason, right? So this is considered as more stable. This is just stable, right? And this is the most stable, right? You can draw few more structures here with this one, right? Few more structures, right? So you can come up with a structure like this as well, some unstable structure, some unstable structure, right? If you are to consider about the contribution towards the resonance hybrid, if you have to think of the contribution towards the resonance hybrid, basically more contribution is from this one, the more stable structure. More contribution is there from the more stable structure, right? Let's consider it as kind of 55% the contribution, right? And this guy is also coming up with some what considerable contribution, right? Considerable contribution like 44% kind of a thing. And the contribution of this thing is actually very negligible, very negligible. But remember, you have some contribution, right? Not zero. Is the highest contribution towards the resonance hybrid. This is also having a considerable contribution. This is kind of a negligible contribution. Negligible, but not zero kind of a contribution. Right? That is why we normally consider these two guys to draw the resonance hybrid. When drawing the resonance hybrid, we just come up with these two guys, right? We consider only these two guys to draw the resonance hybrid because this guy is with a negligible contribution, but we won't say the contribution is zero. Negligible contribution, but some contribution is there, right? Okay, it is negligible, right? So that is why we use these two guys, right? So the ultimate, the resonance hybrid would look like this, right? Some partial wave bond character with these two guys, right? And you will see this kind of a hybrid ultimately. Anyway, right? The contribution of this thing is not zero, even though we consider it as negligible. Negligible means not zero, right? Negligible means something is there, but we don't have to consider that much when drawing the resonance hybrid. That is what negligible means. It is not the zero, right? So contribution from the unstable as well as less stable wave structures are negligible but not zero for the resonance hybrid, right? So as the statement says, the no contribution from the stable, unstable and less stable resonance structures, the statement is false. The statement is false. Negligible but some contribution is there. So statement is false. Right? That is the review for the statement number 6. Right. Okay, let's discuss the statement 7. Right? What it says. See, as the molecular weight is high, CO2 is with a greater boiling point than H2O. As the molecular weight is high, CO2 is with a greater boiling point than H2O. That is what it says. Let's see whether it is true or false. Right? This is regarding the boiling points of covalent compounds. Boiling points of covalent compounds, right? When it comes to boiling points of covalent compounds, right, there are two factors matter, right? There are two factors matter, right? So Two factors matter, right? The first thing, when the delta MW, molecular weight difference between the two comparing stuff, when the delta MW, molecular weight difference, is greater than 50 units. This is a rough value. Huh? When the molecular weight difference is greater than 50 units, right? We say with the species with greater molecular weight is with greater boiling point, right? That is due to the restrictions of thermal motions, right? When you are very heavy, it is very hard for your particles to move. It is very hard for your particles to move, right? So boiling means you need to put the particles apart from each other, right? Boiling means actually you are to convert a liquid to a gas, right? You have to put the particles apart from each other. You have to increase the speeds of the particles. To do those things, when you are heavy, it's become harder. So you need higher temperatures to do so. So boiling points will increase with that, right? So when the molecular weight is high, boiling point is high. Nothing to think. If the molecular weight difference is greater than 50 units, the species with the greater molecular weight is with a greater boiling point, right? So the second thing is considered when the molecular weight difference of the two considering molecules are less than 50. Then we have to consider the strength of secondary interactions. Strength of secondary interactions. So when strength of secondary interactions, when that is high, right, you need higher energy to break the particles, break the bonds between the particles and put them apart. When the strength of secondary interactions is high, that means that your particles are bound together heavily, strongly. So you need some greater temperature, greater energy as thermal energy to break those bonds and put them apart, to boil the compounds, right? So strength of interactions are high, your boiling points become high, right? So those are the two things we have to consider here, right? Let's see what they are saying again. So we are here to compare about the CO2 and H2O. As the molecular weight of high, CO2 is greater than H2O. CO2 and H2O. So we know the CO2, the molecular weight of CO2 is 44, carbon 12, 2 of oxygen, 44. H2O is 18. H2O is 18. So that comes under this category. That comes under this category. CO2, H2O comes under this category, right? Because CO2 is with 44, oxygen H2O is with 18. The difference between the 44 and 18 is less than 50 units. So the two guys comes under this category, right? So we have to discuss about the secondary strength to see which guy is with a greater boiling point. So when it comes to CO2 molecules, as CO2 are nonpolar particles, among the CO2 molecules, among the nonpolar particles, right, among the nonpolar particles, only the London forces appear. London forces appear, right? When it comes to H2O, when it comes to H2O, when it comes to H2O, among H2O molecules, you could think of the presence of hydrogen bonds, can think of the presence of hydrogen bonds among H2 molecules. So as we know, the second interaction strength of hydrogen bonds are stronger than London forces. The H2O is with stronger second interaction strength. So those should be with a greater boiling points, right? So we can see secondary interaction strength of London forces are less than that of hydrogen bonds. So among CO2, you have the London forces. Among H2O, you have the hydrogen bonds. So your boiling points. When it comes to boiling points, the CO2, which is with London forces, should have a lower boiling point than H2O, which is with hydrogen bonds. Right? That is how we are supposed to write copy the boiling points. So the statement says, as the molecular weight is high, CO2 is with a greater boiling point than H2O. The statement is false. Yes, the CO2 is with a greater molecular weight, but what matters here is the second interaction strength, because the molecular difference is not exceeding 50 units. So what matters for the boiling points between the CO2 and the H2O is actually the second interaction strength. So that as H2O is with hydrogen bonds, it is with a stronger second interaction strength than the CO2, which is with London forces, so that the boiling point of H2O is greater than the CO2, right? The statement is false because of the second part, right? Okay, the statement is false. Right? That is a review for your statement number 7. Let's discuss the statement number 8. Right? See, solubility of I2 in NaOH is greater than the solubility of H2O. Solubility of I2 in NaOH is greater than the solubility in H2O. Right. Here we are referring to solubility of I2. At one instance, it is the solubility of I2 in NaOH, and the other instance, it is the solubility of I2 in H2O. Right. Let's see with which solvent system the I2 will dissolve more, right? So this is all about solubility of I2. Solubility of I2, right? So when it comes to solubility of I2 in NaOH, solubility of I2 in NaOH, the thing would look like this in your JQ, no? In your JQ, right? So if you are to think of the NaOH AQ, if you think of NaOH AQ, right, the things are looks like this, no, Lama? So you have some Na plus particles and Cl minus particles, right? You have some ions basically, yeah, which are actually surrounded by water molecules. This is how the system looks like, right? The NaCl aqueous solution, right? So if you have to think of I2 here, right? I2, I'm drawing the I2 molecule. I'm drawing the I2 molecule here, see? right? Now this I2 molecule can form this kind of strong interactions here. What is this strong interaction kind? Right? This is referred to as ion induced dipole interactions. Ion induced dipole interactions. These are ions, species with complete charges. These are non-polar species, that means induced dipoles. So you would observe the ion induced dipole interactions in a system of I2 in NaOH aqueous. Right? Okay. So let's consider the situation with just the water. Solubility of I2. Just think of water in just water, pure water. There, the water molecules are there. Right? These are the water molecules appearing here and there. Right? These water molecules are there, right? And there you could see the I2 trying to dissolve here. Right? Yes, you will form kind of a second interaction. But this kind, this is referred to as water molecules are polar molecules. These are water molecules, polar molecules, dipoles, and this is non-polar molecule, induced dipole. This interaction kind is referred to as dipole induced dipole interactions. Dipole induced dipole interactions. As we know, the ion induced dipole interactions are stronger than the dipole induced dipole interactions, right? Your I2 molecules will trap heavily in this kind of system compared to here. Right? I2 molecules will trap heavily in this kind of system compared to here, as ion dipole interactions are more stronger than the dipole induced dipole interactions. The I2s will bound heavily to these ions compared to just dipoles, the water molecules. Right? So we can say, right, secondary interactions strength. Second interaction strength. Here comes second interaction strength. Ion dipole, ion induced dipole. Sorry, ion induced dipole. Interaction strength is greater than dipole induced dipole. So I2 molecules will trap heavily. Heavily in NaOH compared to pure water. Right? So the solubility of I2 in NaOH is greater than the solubility of I2 in water. Right? So solubility solubility, right? I'll write it here, right? I think it's not okay, right? So we can write solubility, right? I2 in NaOH, right? I'll write it here. I2 in NaOH is greater than the I2 in pure water. right? So we can consider the statement, the solubility of I2 in NaOH aqueous is greater than the solubility of H2O as a true statement. So we can consider the statement as a true statement, right now? So that is the idea about the statement number 8. Let's discuss about the statement number 9. Right. See what it says. Ionization energy of hydrogen can be calculated with the use of the wavelength of last line of Balmer series. Last line of the Balmer series. Right. Is regarding the right hydrogen spectrum and ionization energy. Of hydrogen. Right. So ionization energy means the minimum energy needed for a gaseous atom to release its most loosely bound electron to form a gaseous 1 plus ion, right? That is what is meant by the ionization energy, right? So I'll write it here. Ionization energy is the minimum energy needed to supply, to eject, to remove, let's say remove most loosely bound electron from an gaseous atom to produce gaseous plus 1 ion. That is the ionization energy, right? When it comes to hydrogen, as hydrogen's ground state electron appears at n equals 1, right? To eject that electron out from the atom, we have to excite that electron towards the n equal infinity, right? So you have to provide energy to release this electron, to excite this electron to n equals infinity. That is when the ionization occurs, right? As a radiation, you could apply the energy, right, to put this electron to the n equals infinity, right? Then the ionization occurs. Electron will eject from the atom. So that is what is meant by the ionization, and this energy is referred to as the ionization energy, right? So energy needed to excite the hydrogen's only electron from n equals 1 to n equals infinity is referred to as the ionization energy of H atom. Actually, this energy gap, this energy gap is actually represented by the last line of the Lyman series, right? This energy gap, this delta E, the energy gap is actually represented by the last line of the Lyman series, right? If you are regarding the electronic transition of last line of Lyman series, that is actually last line of Lyman series. Lyman means n equals 1. Towards the n equals 1, the electron should come, right? From the higher energy levels. So the last line, the highest energy gap possible, is coming from n equals infinity to n equals 1. So actually, this energy gap is related to the last line of the Lyman series. Last line of the Lyman series, right? So that is this last line of Lyman series. N equals infinity to n equals 1. This is the electronic transition responsible for the Lyman's last line. Lyman's last line. So see what they are saying. Ionization range of hydrogen can be calculated with the use of the wavelength of the last line of not the Balmer but the Lyman series, right? Last line of Lyman series. So we have to think of the last line of the Lyman series, right? Lyman series, right? Right? This last line. This last line of your Lyman series. If you know the lambda or the frequency of this last line of Lyman series, right, you can come up with the hydrogen ionization energy by applying that value to E is equal to h mu or E is equal to HCO lambda, right? Okay, so ionization energy of hydrogen is given by the last line of the Lyman series, not the Balmer series, right? So we have to take the statement as a false statement as they are indicating something about Balmer series, right? N equals, if the electron is transiting toward the n equals 1, that is all about Lyman series, right? Okay, so your statement number 9 is false. Let's discuss about the statement 10. See what it says. The actual charge of Mg2 plus ion is less than that of PO43 minus ion. The actual charge of Mg2 plus ion is less than that of PO43 minus ion, right? See the concept of actual charge, right? The actual charge and relative charge, right? So if you think of the magnesium 2 plus, think of the magnesium 2 plus, this 2 plus means the relative charge. This 2 plus means the relative charge, right? So your relative charge, that is the plus 2. 2 plus means the relative charge. Then what is the actual charge of magnesium 2 plus? actual charge is 2 into, right, 1.6 into 10 to the power minus 19 coulombs, right? This happens because now you are with two more protons compared to electrons. You have only 10 electrons in the magnesium 2 plus, but you have 12 protons. So due to the presence of excess of two protons compared to the electrons, right, this charge appears. So protonic charge is this. Protonic charge is this 1.6 into 10 to the power minus 19 coulombs. Even the electronic charge is that. When it comes to coulombic charge, you don't have signs. You don't have positive negative signs with the coulombic charge. The protons are coming up with this. Such two protons are in excess. So the actual charge of magnesium 2 plus is this. Right? So let's come up with the PO for 3 minus. So its relative charge is minus 3. PO for 3 minus. Then the actual charge, right? The actual charge, this 3 minus appears because now you have 3 more electrons compared to the protons in this chemical species. Compared to the protons in this chemical species, now you have 3 more electrons. That is why the 3 minus appears. 3 more electrons. One electron carry 1.6 into the power minus 19 coulombs. Such 3 electrons are there. So actual charge of the PO43 minus is this number, right? So I'll take this number as 1, this number as 2. You clearly see this number 2 is greater than the number 1, right? As number 2 here is greater than the number 1, this value is greater than this value. This is 1.6 into 2 minus 3 minus 19 into 3. This is 1.6 into 2 minus 19 into 2. This value is greater than this, right? So we can say, so because actual charge the magnesium 2 plus charge is lesser than, so I'll write it here, no? I'll write the thing like this, so no confusion then. 2 is great, right? So 1 representing the magnesium's charge and 2 representing the actual charge of phosphate ion. So phosphate ion means with a greater actual charge than the magnesium 2 plus ion. The statement 10 says the actual charge of magnesium 2 plus ion is less than that of P of 3 minus ion. So that is true. This guy's actual charge is less than that of P of 3 minus, right? So the statement is true. Statement is true. Right? So that is the review for the statement number 10. Let's discuss about the statement 11. See what it says. When two species are with the same shape, their electron pair geometry should be the same. Not necessary, no? Right? See? So with the same shape, you can think of different electron pair geometries as well, right? Same shape but with different electron pair geometries. See, so you can think of, right, linear shape. So linear shape coming from linear electron pair geometry, could come from linear electron pair geometry. Electron pair geometry is linear, or we could think of some linear shape coming from trigonal bipyramidal geometry as well, right? See, XCF2, the electron pair geometry, is equal to trigonal bipyramid, right? So we have such shapes, right? The same shape, but with different, coming from different electron pair geometries, right? So even we could think of bent or angular shape. See, angular shape could appear from a trigonal planar geometry. See, SO2, electron pair geometry is trigonal planar. Or angular shape could appear with a tetrahedral geometry as well. So you could think of same shaped stuff but with different electron pair geometries. So the statement says when two species are with the same shape, their electron pair geometry should be the same. Should term appears. So no need of such. So you could think of same shaped species with different electron pair geometries as well. So the statement is false. So the statement is false. Right? So that is the review for the statement number 11. Let's discuss about the statement 12. See what it says. Oxygen state and the valency of nitrogen in NH4 are -3 and 5 respectively. Right? See the oxygen state and the valency. What is oxygen state? Oxidation state. Right? That is the charge of considering atom if all the bonds are considered to be ionic. Right? Let's discuss about the NH4 plus, the oxygen state. So this is the NH4 plus. Right? If you have to assume all of these bonds are ionic, no covalent component, if all the things are ionic, then how it looks like? Right? If all these bonds are ionic, right? No covalent counterpart, right? So that the plus charge always appears, no, right? This plus, right? So these two electrons, if all the bonds are ionic, these in it form, if all the bonds are ionic, right? The electrons are attracting towards the more alternative atom, which is nitrogen. So nitrogen, right, gets both the electrons. Even the hydrogen electron will gain by the nitrogen. So nitrogen get a negative charge. As hydrogen loses its electron, it's get a positive charge. With all the four covalent bonds, this kind of a charge separation occurs if all the bonds are considered to be ionic. Right? So if you have to come up with the charge around the nitrogen in this case, you clearly see it is -1, -2, -3, -4, and is +1. So the charge around that nitrogen is -3. So the oxygen state of nitrogen here is -3. Normally oxygen states are denoted inside brackets. The oxygen state of nitrogen is -3. Right? So next stuff is about the valency. Valency. What is meant by valency? That is the number of electrons participated from considering atom when forming the chemical species. Right? Let's consider the NH4 stuff, NH4 plus again. Right? So we clearly see from nitrogen this electron, this electron, this electron, and this electron. These 4 electrons are participated in forming covalent bonds. Right? To form covalent bonds, right? 4 electrons are participated. To give this +1 charge, to give this +1 charge to the nitrogen, to give +1 charge to nitrogen, 1 electron has been removed. 1 electron has been removed, right? So its contribution is also there. Without that contribution, you can't form the N plus there. So total number of electrons participate from the nitrogen forming the NH4 plus is actually 5 electrons. 5 electrons. 5 electrons. So your valency is equal to coming up with 5 electrons. Right? It's coming up with 5 electrons. Right? So we can say your valency is equal to 5. Valency is equal to 5. Number of electrons participated from the considering atom, right, when forming the chemical species, right? So the electrons participated in forming covalent bonds is referred to as, that valency is referred to as the covalency. Here the covalency is 4, and here the charge valency, that is 1. That is how the total valency becomes 5. It is how the total valency becomes 5. Right? So when considering ammonia, right? Your oxygen state is -3 and the valence is just 5. You don't have any signs, with the valency, but with the oxygen state, definitely you should come up with a sign, right? So that is the review for the statement number 12, and we have to take that thing as a true statement. Right now, that is all about the statement 12. Let's discuss about the statement 13. See what it says. Information on degenerate orbitals is given by magnetic quantum number. Information on degenerate orbitals is given by magnetic quantum number, right? So this is statement 13, right, regarding the quantum numbers. Right? You know, quantum numbers are used, right, to identify electrons by identifying their energy, sub-energy levels, and the orientation in space, as well as the speed, even the spin of the electrons. By identifying those properties, the quantum numbers are used to identify electrons, right? Okay, so normally in an atom, right, to correctly identify an electron, right, we need, right, completely identify an electron, completely get the information of the electron, we need 4 quantum numbers, right? 4 quantum numbers are used. So those are the n value, the principal quantum number, L value, the azimuthal quantum number, ML value, magnetic quantum number, and the MS value, the spin quantum number. Here the question is regarding the ML, right, which is the magnetic quantum number. It is referred to as the magnetic quantum number. What are the important stuff we should know about the magnetic quantum number? Now, the magnetic quantum number, ML, right, is used to identify the degenerate orbitals, right? This is ML values are used to identify degenerate orbitals. What are degenerate orbitals? Degenerate orbitals are the orbitals with same shape and energy, normalized in a same subshell, but with different 3D orientation in space. Those are degenerate orbitals. So to identify the degenerate orbitals, we use the magnetic quantum number. What else we should know? Right? With the ML values, you have a selection rule. What is the selection rule there? So the selection rule is you can't take any ML value for a given L. So ML values are restricted with this selection rule. That is, you can take from -L to along with 0 to +L. Those are the values you can take for ML. So what else we should know? Actually, the number of ML values. The number of ML values gives the number of orbitals, number of degenerate orbitals in a considering subshell. As an example, if you need an example, you can say we know with the S subshell only one orbital is there. That means only one ml value is there with this subshell. With the P subshell, you know, Px, Py, Pz, three orbitals are there. So you have three ml values, ml minus 1, 0, and plus 1, with the L equals 1, which is the L value of the P orbitals. When considering d orbitals, d subshell, the L value is L value is 2 for the d subshell. So you have minus 2 to plus 2 along with 0. You have such 5 ml values, minus 2, minus 1, 0, plus 1, and plus 2. 5 ml values with d subshell. That means 5 orbitals are there in a d subshell. So number of ml values gives number of degenerate orbitals in a considering subshell. Right? These are the stuff we should know about the magnetic quantum number, right? So let's go to the statement again. It says information on degenerate orbitals is given by magnetic quantum number. Yes, the statement is true. The statement is true. This is all about degenerate orbitals, the magnetic quantum number, and the orientation of them in space, 3D space. Right? Okay. This is actually the review for your question or the statement number 13. Right? Let's discuss about the statement number 14. Right? Lewis theory does not discuss the concept of hybridization. See, right? Basically, this is regarding the hybridization, right? Hybridization, right? When it comes to Lewis theory, it is actually based on orbits, based on orbits of Bohr theory, right? Based on orbits of Bohr theory. First energy level, second energy level, 2, 8, 8 stuff, based on the orbits of Bohr theory, right? When it comes to hybridization, it is what? It is discussing the mixing of atomic orbitals, right? The atomic orbital concept that comes with the quantum theory. Atomic orbitals concept comes with the quantum theory. Mixing of atomic orbitals, the 3D space, the most probable 3D space where you can find out an electron, that is an atomic orbital, right? Mixing of atomic orbitals to give identical orbitals with, actually we call it as molecular orbitals. Same shape, pattern, energy, but differs in orientation in 3D space. Actually, hybrid orbitals are degenerate orbitals, right? Hybrid orbitals are degenerate orbitals. The energies are same, shapes is same, but the orientation in space is different, right? So, mixing of atomic orbitals to give identical molecular orbitals with same shape and energy is referred to as the hybridization. Basically, to discuss about the bonds in 3D space, we need this concept, right? So you clearly see the Lewis theory is based on the Bohr theory, the orbits and the Bohr theory, and the hybridization is based on the atomic orbitals. sp hybridization, sp2 hybridization, sp3 hybridization, s orbitals, p orbitals, d orbitals, sp3d hybridization. Orbitals are involved there, right? Here just the orbits, right? Examples, right? S orbital mixed with a p orbital. Got the idea, no? Right? So the statement Lewis theory does not discuss the concept of hybridization. The statement is true. You don't have the knowledge of orbitals at the Lewis theory, which is based on just the orbits of Bohr theory. Right? So the statement is true. The statement is true. You need to know the concept of orbitals to discuss about the hybridization. S orbitals, p orbitals, d orbitals. Right? That is the review for your statement 14. Let's discuss the statement 15 of your in-term revised tree. See, in an atom filled with electrons, 4s electrons are with greater energy than 3d electrons. In an atom filled with electrons, 4s electrons are with greater energy than 3d electrons. Right? So we are considering an atom filled with electrons. Right? So we know the best example I can think of, right, giving you a good explanation is actually think of a iron formation. Think of iron formation from D block species. Think of iron formation from D block species, right? So I'll take some example, right? I'll take some example. First ionization of let's say iron. It's a D block element, right? Think of that. So iron counts with this configuration. Iron, as it is the 26th element, right? It comes with argon configuration, right? 3d6 and 4s2, right? So when forming cations, when forming cations, when forming cations, when forming cations, Fe plus Cl, we are supposed to release the electron from the outermost shell, electron from the outermost shell, So electron will be released when forming the Fe plus from here, right? When forming cation, electron from outermost shell is released, right? So that the electron configuration of Fe plus is going to be what? 3d6 4s1. Outermost shell is released, right? So actually what this means, right? Ionization means you are supposed to eject an electron from the atom. That means you are supposed to, right? You are supposed to excite an electron to the n equals infinity. You are supposed to excite an electron towards the n equals infinity from a lower energy level, right? So if you are to think of two energy levels which is very close to each other, you think of the two energy levels, the occupied last two energy levels, which are very close to each other. Towards here, energy increases, huh? Right? So ionization means the releasement of this electron towards here. This is ionization. This ionization is what is meant by ionization. The lowest, the minimum energy needed to eject an electron. It is not about ejecting an electron from here to here. Ionization is the minimum energy needed to eject an electron. It should be the electron from the energy level with the greatest energy. So according to this, it says the 4s electron is released. It says the 4s electron, one of the 4s electrons are released. That means 4s angular should be with a greater energy than the 3d, than the 3d, right? Than the 3d, right? So your 3d is with 6 electrons. 4s it's with 2 electrons. So they are saying the ionization occurs by a 4s electron. That means 4s energy shell is the energy level is the closest to the n equals infinity. So this says that confirms that the 4s is with a greater energy than the 3d in an atom filled with electrons. In an atom filled with electrons, right? So again, let's go to the statement. It says in an atom filled with electrons, 4s electrons are with greater energy than 3d electrons. Yes, the statement is true. The statement is true. Right? So that is the review for the statement 15. Let's discuss the question number 16. Right? They have provided you the Br2, CO2, IgL and Ne, the boiling points. Right? Again, we have to discuss about species with second interactions. No? So these are not metallic stuff. These are not ionic stuff. So we have to discuss about the boiling points of covalent stuff, no? The particles connected via secondary bonds, right? So two things matter. The first thing is, right, the molecular weight difference, no? right? First consideration, two considerations. The first thing is molecular weight difference. When delta MW is greater than 50, right? What we know is when molecular weight increases, right, boiling point increases, right? The second thing is actually when the difference is less than 50 units, right? When secondary international strength is high, boiling points are high. Those are two considerations, no? Right? Let's discuss. Right? According to this, we have to select the variation of boiling points of these four guys. Right? Okay. So I'll write the molecular weights. So bromine carries 80. 80 into 2 is 160. The molecular weights, right? CO2, it is 44. 12 and 2 of 16, 32 and 44. These are the molecular weights I'm just marking. The ICL, I didn't carry some 127 and CL is 35.5. So it is going to be, right, 162.5 kind of a thing. The neon, right, neon basically carries some 20, no? Helium neon 10th atom means you can take it as 20. These are G mole minus 1 value, right? The molecular weights, right? So according to this, according to the criteria 1, according to criteria 1, and we can say the two guys, these two guys are greater with boiling points than these two, right? According to molecular weight difference, right? We can say, so Br2 and IgL are with greater molecular weights compared to CO2 and neon. Clear, no? The molecular weight difference is greater than 50 units, right? Then these two, right, can be compared with use of the second fact, right? These two can be compared with use of second fact. 2, right? These two guys are with London forces, and we know when the molecular weight increases, the London force strength increases. London force strength increases. So London force strength is high with the CO2 than the neon, right? So neon is with the smallest, and CO2 is with the highest. As London force strength increases with greater molecular weight, right? So when it comes to these two, again we have to come up with the second fact, right? This is coming up with the dipole-dipole interactions. Is just coming up with London forces. So dipole-dipole interaction containing species is with a greater boiling point than the species with London forces, because the secondary strength of dipole-dipole interactions are greater than that of London forces, right? So these guys are with dipole-dipole interactions is with London, the Br2. So interaction strength is greater with dipole-dipole interactions compared to London, right? So as this is a polar molecule, it possesses dipole-dipole interactions. With non-polar species, only the London forces appears. So the thing is like this. So finally, we can come up with the answer. So ICL is with a greater boiling point. So Br2 next, The smallest is with neon, and CO2 is with a greater one than the neon, right? So this is the answer, right? That is the review for your question number 16. Let's discuss about the question number 17, right? So you have carbonate, carbon monoxide, carbon dioxide, and the CuCl2, and they are asking you the increasing order of the affinity of carbon, right? When considering the same atom, right, the affinities will vary according to the chemical environment, right? Affinities will vary according to the chemical environment, right? Electronegativity varies according to chemical environment, right? What are the four considerations there, right? All right, like this. The first consideration is the hybridization. When its character of hybridization is high, right? Your affinity is high. Right? The second factor, when these characters are the same, we have to come up with the second factor. The second thing is the charge on the atom. When positive charge on atom is high, your affinity is high. When both are the same, you have to come up with the oxidation state. Oxidation state, right? When positive nature of oxidation state is high, your affinity is high. If all the three factors are same, then you have to decide according to the surrounded atoms, the connected atoms, what it says, the effect of the connected atoms, right? When electronegativity of connected atoms is high, your considering atoms electronegativity is also high. Electronegativity of considering atom is also high. So this is also known as the electron deficiency. If electron efficiency of your considering atom is high, your electronegativity of considering atom is high, right? See, these are the major four considerations to discuss about a variation of affinity of a given atom, right? See, so that we have to come up with the Lewis structures to come up with the S character, CO32 minus, right? Lewis structure is this, right? So carbon monoxide, this is the Lewis structure. CO2, then you have CuCl. So right, you clearly see the hybridizations. This is P, this is also Sp, this is P2, 1, 2, 3, sigma and lone pair count gives you 3, that means sp2. This is also sp2, sorry. Sigma 1 and lone pair count of the considering carbon is 3 units, sp2, right? sp2. So definitely these two guys are with greater utilities than these two guys, right? According to the first factor is correct. We can say, right, carbon monoxide. So right, I like this. Carbon monoxide and carbon dioxide guys are with greater utility than the carbonate and the COCl2. According to the first factor. Then we can think of, we can place these two guys according to the second factor, positive charge of the atom. When it comes to positive charge of the atom, so this is carrying -1, it's carrying -1 charge with carbon. This is carrying 0 charge with carbon. So positive energy is high. So utility of CO2 is higher than that of carbon monoxide. The charge on the atom, when the positive charge is high, utility is high, right? So we can locate the two guys. The CO2 is with a greater utility than the CO, right? Now let's move towards the carbonate and the CO2 Cl. With these two guys, both have the same charge. Both have the same charge. Then we have to come up with the oxygen state. Oxygen state, right? Here, with this one, the oxygen state of carbon is +4, as well as with this one, the +4. Oxygen states are also same with the carbonates and the CO2Cl, the carbon. Then we have to think of this one, electron deficiency. Here, oxygens will attract the electrons from carbon, 4 bonds of carbon. So compared to 2 bonds with oxygen and 2 bonds with chlorine. So the electron deficiency of this carbon is high actually, because severe electron attractions from the oxygens compared to chlorine here, right? So electron deficiency here is less with this carbon. So what we know is, greater your electron deficiency, greater will be the electronity of your considering atom. So right, the carbonate is the greater electron deficiency, so as the electronity compared to CO2Cl, right? So that is the situation with the electronity of carbon, right? Okay, so that is review for the question number 17, right? Let's complete the stuff. Okay, the question number 18. This is regarding the electron gain energy, right? So what are the things we should know? Basically, first we should know there are 3 atoms with endothermic electron gains, right? Those are the ones with the lowest first electron gains. What are those? Beryllium, magnesium, and nitrogen. But those 3 guys are not there. So we are discussing about species which are with exothermic electron gains, right? So when it comes to exothermic electron gains, when it comes to species with exothermic electron gains, exothermic, right? Negative electron gains. What you should know, the group 17s are the ones with the greatest first electron gains. They are also, the chlorine is the one with the greatest value, like this. Then you have the sulfur, oxygen. All the other atoms are with less electron gain energies than these guys. So when it comes to exothermic electron gains, the highest values are with group 17. Highest values are with group 17s. Next highest values are with group 16. Right? The reason is that, what was the reason? Because these guys are the ones with greatest effective charge, right? So that it is easy to attract the electrons. Right? This is next greatest. This is the reason, right? Okay. So that is what you should know. You should know the first 8 guys with the greatest electron gain energies, right? So with this, you can complete the stuff, right? So the one with the greatest first electron gain is the chlorine, then fluorine, group 17s, then you have the group 16 guys, right? So the sulfur and the oxygen, right? So normally going towards down, the electron gain decreases as the atomic size increases, right? But chlorine is with a greater value than the fluorine, and sulfur is with a greater value than the oxygen. The reason there is some repulsions will occur as the oxygens and the fluorines, the group 2, second row guys are too much small. That thing also should be known, right? That is there in your notes, right? Go through that as well. So this is the variation, and you should know the reason for these two as well, right? This situation and reason for this thing also should be known. The too much small situation with the second row atom compared to the third row atom, right? Always the first electron gain of third row atom is greater than the second row atoms, that of second row atom, right? Should know the reason as well, right? So that is the review for the question 18. Let's discuss about the question number 19, right? This regarding the first ionization energies, right? So those of nitrogen, sodium, phosphorus, and argon, right? See, what are the considerations? First, you should know the I1 minimums, right? The considerations. First, you should know the I1 mins and I1 max. I1 minimum values appears with the group 1s, which are more keen to release the first electron. So less energy is sufficient for that. So that is coming up with the greatest group 1, right? Potassium, right? Sodium, and the lithium. Those are the ones with the, right, smallest minimum values with I1. Then I1 max values also should be known. I1 max values comes with the noble gases, because those are the ones which are not keen to release electrons, because those are with a stable compression. So the helium is the one with least keenness towards releasing the electrons, right? As it is the smallest, right? So it is the one with the greatest first ionization, right? Then you have the neon, and then special guy, the VIP guy appears, the fluorine, Even though it is not a noble gas, it appears, right? It's a VIP situation, and argon. So these are the first four guys with the greatest personalization, right? So out from these, you are supposed to come up with some values first of all. So you have such in the form of argon. So argon is coming up with the greatest side, right? So argon should be the one with the greatest personalization, right? Then after this, right, we are referring to the zigzag pattern, zigzag pattern along a period, right? Okay, so we can first of all, before that, we can locate the sodium as well. No? Sodium is coming with the minimum values. No? Sodium can be also located, right? This is coming up with a minimum. It's coming up with a maximum, right? Okay. So the zigzag. So you have the sodium and phosphorus both coming up with the third row. Sorry, so nitrogen phosphorus, nitrogen phosphorus. So not hard, no nitrogen phosphorus. Even we don't need the zigzag to locate the nitrogen phosphorus, right? So no need of thinking of zigzag even. So nitrogen, right, is a small atom and phosphorus is a large atom, right? So you can use the pattern along a period. Sorry, along a group, along a group. So when going down, as the electron is far away from the nucleus, when going down, so it is easy to release the electron, right? This electron resides more away from nucleus. So releasing electron becomes more easy. This change will be sufficient. So with that, you can locate the nitrogen and phosphorus. So nitrogen is with a lower first ionization than the phosphorus. Sorry, phosphorus is with a lower first ionization than the nitrogen. Right? As phosphorus is large and nitrogen is small. Right? No? So the answer is going to be like that. Sodium, phosphorus, nitrogen, and argon for the question number 19. Right? The answer is clear. No? Right. This is regarding the question number 20, right? This is regarding actually the melting points of the ionic compounds, right? Let's see what matters, right? This is about the melting points of ionic compounds. So when it comes to ionic compounds, melting points will be decided by the ionic bonding strength. Ionic bonding strength. So for the ionic bonding strength, the porosity and the polarizing power of the anion and the cation will be affected, right? So when it comes to cation, right, when the Q plus is high, R plus is low, its polarizing power will be high, right? When it comes to anion, its Q minus is high, R minus is high, its polarizability is high. When these two things happen, right, polarization of the ionic bond increases and covalent character increases, so that the ionic character decreases. Ionic bond strength decreases. With that, your melting points will decrease. The particles are not bound heavily now. The ionic bond strength is low, so you can put them apart easily, right? When the porosity power is high, porosity is high, the melting points becomes low, right? This is the idea. So let's consider this to come up with the answers, right? So first, let's consider the ones with the same anions, right? The anions are same here. Considering KCl and NaCl, right? KCl and NaCl. Let's consider those two things, right? KCl and NaCl. The K plus and the Na plus. So K plus is larger and Na plus is small. K plus is larger and Na plus is small, right? This is ice. I'm not going to consider about the chlorine because that is common to two stuff, right? So as ice is like this, so your porosity power of K plus is smaller than sodium plus. So the one with the greater melting point, sorry, the one with the smaller melting point should be the one with the greater porosity power, inverse relationship. So because of more melting points, so one with the smaller porosity power is with a greater melting point. One with a greater porosity power is with a smaller melting point. So the inverse, right? It is about the KCl and NaCl. What about the other two? These two guys, where the fluorine is common. Kf and RBF. So let's consider the K plus and the RB plus. Rubidium resides more down in your group 1 compared to potassium, sodium, potassium, rubidium, right? So the porosity, right, of K plus, sorry, this is not the porosity power of K plus is higher than the rubidium plus, and this is smaller, so your melting point, the Kf, is a lesser melting point than the RBF, right? Up to now, the question is solved. See, still we are unable to come up with which one is the greatest, no? So let's compare the ones, the highest ones here, the KCl. So from what we have to compare here. So yeah, basically the two guys are related from the K here, no? Let's compare with this one. You have the K here as well as K here. So out of those two guys, right? The KCl and the KF. If you consider these two guys, what you can see, right? So the cation is same. You can compare the anion, right? When comparing the anion, right? So you can compare the anion there. When comparing anion, the KCl and KF, no? When comparing those two, right? The size of Cl minus is larger than size of F minus. So porosity of Cl minus is larger than F minus. So we can say the melting point when the porosity is larger, the melting point is smaller, right? So the KCl's melting point will be smaller than the melting point of Kf, the inverse relationship with the porosity as well as with the porosity power for the melting points, right? So this says even the highest of this pair is with a lower value than the lowest of this pair, right? So the RBF should be the highest, and then the KF. These two guys should come with the lower values there, right? The KCL is here and the NaCl is the lowest, right? So that is going to be the review for your question number 20, right? Just complete the stuff. Right? So with this, we will wind up the session for today, right? This is about the interim revised paper number 3, right? So we'll meet with the next interim revised paper next week. Goodbye then.